In this problem, we need to simplify the expression given by 1 plus I raised to the power of n plus 1 minus I raised to the power of n, and we will be using the simplified value to obtain the value for n equals to 8. So let's begin. First, we'll start with 1 plus I. We'll have to convert it to its polar form. In order to convert it to polar form, that means it has to be the form r of cosine theta plus I times, where I is iota, times sine theta. So to find out the value of r, all we have to do is we'll take the square root of the real part, square the real part, add it to the imaginary part, square it, and we'll take the square root, which is going to give us the value square root of 2. Then we'll also have to find out the argument. So let's call this as our complex number z1. So argument of z1 will be equals to the inverse tangent of the imaginary part, which is 1, divided by the real part, which is 1. So we have the inverse tangent of 1, and we know that the 1 is actually the tangent of pi over 4. So tangent inverse of tangent of pi over 4, that simply gives us pi over 4. So that means our complex number z1 can be represented as square root of cosine of pi over 4 plus iota times sine of pi over 4. Similarly, we'll consider our second complex number z2, which is given by 1 minus iota. So this will be equals to r of cosine theta plus I sine theta. So here also we'll have to find out. So let's call it r of cosine phi plus iota of sine phi, and this be r1. Since we have already used the two symbols, so r1 will be equals to, we'll take the square root, and then inside the square root we will square the real part and add it to the square of the imaginary part, which is also going to give us the value square root of 2. And then we'll find out argument of our complex number z2, which will be equals to inverse tangent of the imaginary part, which is -1, divided by the real part, which is +1. We have tangent inverse of -1. Now that gives us tangent inverse of negative of 1. 1 means we have tangent of pi over 4, but we know that the tangent is an odd function, so we can absorb the negative sign within, and we can rewrite it as tangent of negative pi over 4. The tangent inverse of tangent of negative pi over 4 is simply going to give us negative pi over 4, such that our complex number z2, when we express it in the polar form, this will be equals to square root of 2 multiplied to cosine of negative pi over 4 plus iota times sine of negative pi over 4. Fine. So we have obtained the value. We can also further simplify this, where we have square root of 2 multiplied to cosine of pi over 4. That's because cosine is an even function, so cosine of negative pi over 4 is simply positive cosine of pi over 4. However, sine of negative pi over 4 will be negative iota times sine pi over 4. The reason behind this is that sine is an odd function. Now what we'll do, we will raise our complex number z1 to the power of n. So that means we have square root of 2 whole raised to the power of n multiplied to cosine of pi over 4 plus iota times sine of pi over 4 whole raised to the power of n. Similarly, we'll also raise z2, our complex number, to the power of n. So that means we have square root of 2 raised to the power of n multiplied to cosine of pi over 4 minus iota times sine pi over 4 whole raised to the power of n. We have done this so that we can easily apply the de Moivre's theorem, which states that whenever we have cosine of theta plus iota times sine theta, if this is raised to the power of some number n, then we have cosine of n theta plus iota times sine n theta. So in both the two cases, our complex number z1 raised to the power of n and z2 raised to the power of n. So z1 raised to the power of n, it is actually our complex number 1 plus iota whole raised to the power of n. So this is equals to square root of 2 whole raised to the power of n multiplied to cosine of n pi over 4 plus iota times sine of n pi over 4. And our z2 complex number, so this is, so let's label this as number 2. We have 1 minus iota raised to the power of n, so this will be equals to square root of 2 whole raised to the power of n. So this will get multiplied to cosine of n pi over 4 minus iota times sine of n pi over 4. So let this be equation number 2. Now what we'll do, we'll add 1 and 2 together. So adding 1 and 2 2 together. So this is going to give us 1 plus iota whole raised to the power of n plus 1 minus iota whole raised to the power of n. So in the right hand side we have square root of 2 whole raised to the power of n. So this is common to both of them. And within the parentheses, when we combine them, our imaginary part will get cancelled out because they are additive inverse of each other. So we have 2 times cosine of n pi over 4. Now square root of 2, this can be also written as 2 raised to the power of half whole raised to the power of n. And this is multiplied to 2. We have cosine of n pi over 4. So if we combine these two terms, so this will be equals to, we have 2 raised to the power of n over 2 plus 1 multiplied to cosine of n pi over 4. Hence we have obtained the simplified form of a given expression. Now what we'll do, we'll replace the value of n with 8. So let's consider n to be equals to 8 such that we have 1 plus I raised to the power of 8 added to 1 minus iota raised to the power of 8. So this will be equals to 2 raised to the power of 8 over 2 plus 1 times cosine of 8 pi over 4. Now we have 2 raised to the power, so 8 over 2, that's 4, 4 plus 1, so that's 5. So we have 2 raised to the power of 5 multiplied cosine of 2 pi. The cosine of 2 pi, this value is 1, so we are left with 2 raised to the power of 5, which final value is 32.